Okay, let us begin with a work done by a variable force. Okay, a force which has, yes, it's a magnitude constant that is called constant force. And work done by a constant force is nothing but a product of force and displacement in the direction of force. But in some cases, a force changes its magnitude gradually, or even it changes its direction also. So, if in such cases, when force changes its magnitude, direction, or both, so that particular force is known as a variable force. And so, we have to deal with now work done by a variable force. So, variable force means force which changes its magnitude or direction or both. Remember. बघा आपण आता एक साध्या एक्झाम्पलवरनं आपण हे समजून घेऊयात. बघा इथे लाईन दिसते. सो दिस इंडिकेट्स व्हॉट? दिस इंडिकेट्स अ कॉन्स्टंट फोर्स. देर इज नो चेंज इन द मॅग्निट्यूड ऑफ फोर्स ड्युरिंग अ डिस्प्लेसमेंट. बघा हा फोर्स वर्सेस डिस्प्लेसमेंटची डायग्राम आहे. तर इथे आपल्याला दिसतंय okay, displacement is taken along x-axis, f is taken along yes y-axis, but this line indicates a constant force. तर या केसमध्ये आपण घेतलं वर्क डन इज इक्वल टू डायरेक्टली दिस फोर्स व्हॅल्यू डेल्टा एक्स. सो वी हॅव डन दिस. पण बघा व्हेरिएबल फोर्स जस्ट लाईक हे कर्व दिसतंय. जर असा व्हेरिएबल फोर्स आला तर आपल्याला काय करावं लागेल? सो फर्स्ट ऑफ ऑल आपल्याला करावं लागेल, इफ सपोज दिस इज अ स्टार्टिंग पॉइंट, if suppose this is starting displacement xi suppose, and this is a end displacement. Okay, this is a end displacement. बघा आता ह्याचा एरिया मला काढायचा आहे. व्हॉट इज दिस एरिया ऑफ दिस डायग्राम इज नथिंग बट वर्क डन. आपण माहिती आहे एरिया ऑफ दिस एफ एक्स इज नथिंग बट व्हॉट? वर्क डन. ओके, सो दिस एरिया इज रेक्टँगल. सो एरिया ऑफ दिस रेक्टँगल गिव्स अ फायनल आन्सर. हे केलं आहे आपण. पण बघा आता असा कर्व आला म्हणजे नथिंग बट अ व्हेरिएबल फोर्स. सो अशा वेळेस आपण इंटिग्रेशन शिकताना आपण पाहिलं आहे की आपण याला छोट्या छोट्या अशा रेक्टँग्युलर स्लायसेसमध्ये डिवाइड करू शकतो. सपोज वी हॅव डिवायडेड लाईक दिस. समजा एवढ्या आपण स्लायसेसमध्ये याला काय केलं? येस, वी हॅव डिवायडेड इट. ओके, असे 4 रेक्टँगल असे स्लाइस बनवले. लेट अस टेक एनी येस आउट ऑफ दिस. इफ यू कन्सिडर दिस ए, दिस बी, दिस सी, डी, ह्या सगळ्यांची जी डिस्प्लेसमेंट आहे किंवा ह्या सगळ्यांची जी साईज आहे समजा ती 1 आहे. दॅट इज सपोज अ डेल्टा एक्स हियर. ओके, डिस्प्लेसमेंट कॅन बी डिवायडेड इंटू अ लार्ज नंबर ऑफ स्मॉल इक्वल डिस्प्लेसमेंट्स डेल्टा एक्स. ड्युरिंग अ स्मॉल डिस्प्लेसमेंट डेल्टा एक्स व्हॉट हॅपन्स? द फोर्स कॅन बी अज्युम्ड अ कॉन्स्टंट. म्हणजे हा जो फोर्स आहे हा स्मॉल डिस्प्लेसमेंटला आपण काय केलं? कॉन्स्टंट अज्युम केला. सो यू कॅन अज्युम कॉन्स्टंट. सो देन वर्क डन. सो इन दिस केस वर्क डन इज सिम्पली गिवन बाय this work done is given by yes, this is area of rectangle ABCD. Small rectangle साठी काय घेतलं आपण? F into delta x. In this case this total is a delta x, so that's what taken. Same घेतला आपण. पण आपण इथे एक रेक्टँगल ची डील करतोय का? We are dealing with the number of rectangles from this xi to x final, from the starting displacement to end of displacement. So for such cases we have to take summation of the small work done from xi to xf, xi to x, nothing but this becomes sum of areas of all rectangles. Because sum of areas of all rectangles, sum of these rectangles, small rectangles over all the displacement. म्हणजे आपण काय केलं? एक रेक्टँगल ABCD घेतला बाहेर ज्याचं डिस्प्लेसमेंट डेल्टा एक्स आहे आणि या सगळ्यांचा डेल्टा एक्स डेल्टा एक्स डेल्टा एक्स डिवाइड केलं. म्हणजे टोटल याला आपण एक्स म्हणूयात, टोटलला एक्स म्हणूयात. ओके, अँड दॅट इज डिवायडेड इन दिस स्मॉल पार्ट ऑफ डेल्टा एक्स, डिवायडेड इन दॅट वे. सो दिस गिव्स अस डब्ल्यू इज इक्वल टू वर्क डन इज इक्वल टू समेशन एक्स आय टू एक्स एफ एफ डेल्टा एक्स. सो ऑल टुगेदर इट बिकम्स लाईक दिस. म्हणजे हा जो आहे इथे जर आपण एक लाईन काढली, सो दिस इंडिकेट्स अ वर्क डन. ओके, दिस रेक्टँगल indicates a work done. Okay, this indicates a work done. So area of this graph indicates work done. बघा आता याला आपला कलेक्ट करायचं आहे आणि हा डेल्टा एक्स आपण अजूनही बघा इथे गॅप आहे, अजूनही इथे गॅप आहे. सो वी आर नॉट कॅल्क्युलेटेड एक्झॅक्टली इट्स व्हॉट वी वॉन्ट. बट इन सच केसेस आपल्याला काय करावं लागेल? लिमिट इफ यू पुट लाईक दिस. बघा मॅथमॅटिक्स शिकताना पाहिलं आपण, if you put delta x tends to 0, very very small, number of rectangles tends to be yes infinite and very small, म्हणजे अजून छोटे छोटे रेक्टँगल जर तयार केले तर हा गॅप सगळा भरून निघणार आहे. So we are going to moving towards the correct value. So summation approach is, so in this way what happens here, we know that from mathematics, that is if you take limit and this delta tends x to 0, so that gives us a summation xi to xf, okay, that is f delta x, and this gives a direct formula, that is a limit integration xi to xf f dx, okay, f dx. Okay, so work done is given as integration of f into dx, okay, f into dx, that gives a value work done for the variable force. So conclusion is what, for a varying force which changes in magnitude or direction or both, whatever, work done is equal to the definite integral of the force over the given displacement. Okay, this is a definite integral of f dx, nothing but. So that gives a mathematically from between the limit initial to final f into delta x, that gives a work done. So using this mathematical expression we can solve number of problems on the variable force, and also graph is with you. So graphical form is also there. So we have concluded what, area of the fx diagram is gives work done, and work done is nothing but given by a limit integration, definite integral between limits xi and xf f dx. So this gives a variable force. So let us solve some examples on this. And another thing, if force varies both in magnitude and direction, then this work done or this formula becomes like this. So I'm writing here W is equal to integration from xi to xf. Okay, there is no any doubt. So f dx cos theta. Okay, if it is vary in magnitude and direction, then you can use this type of relation to get a work done by a variable force. A 2 kilogram particle starts at the origin and moves along the positive x-axis. The net force acting on it measured at intervals of 1 meter is 27.9, 28.3 up to 27. So what is the total work done on the particle in this interval? So what is given to you? Yes, for every 1 meter, the forces are given to you. That is 27.9 Newton, 28.3 Newton, 30.9 Newton. So we want to calculate here work done. So work done can be calculated by definite integral from initial displacement to final displacement. But see, in this case, there are for each interval forces are given to you, which is varying like that 27.9, 28.3, 30.9. So it is going up and down like that. So we have to simply add these work done for each interval. That is, interval means displacement everywhere is same, and forces are in the direction of force because net force is given to you. So we have to do this simple mathematical treatment for such problem, and that is work done. Okay, work done W is equal to summation Fi and whatever xi. Means very simple, you have to multiply each force by displacement, like this 27 point into 1 plus 28.3 into 1 plus this 30.9 into 1 plus, so take next 34 into 1 plus 34.5 into 1, that is 46.9 into 1 plus 48.2 into 1 plus 50 into 1 plus 63.5 into 1. So this is lengthy addition, 13.6 into 1 plus 12.2 into 1 and 32.7 into 1 Okay, whatever it remains, plus 46 point into 1 and 27 into 1. So this total addition gives you a final answer. Okay, so this addition gives us final answer. Addition gives 469.3 joule. Okay, 469.3 joule. So this gives a simple yes addition of each work done. 416.3 joule is the answer for such question. A woman pushes a trunk on a railway platform which has a rough surface. Okay, means there is a friction. She supplies a force of 100 Newton over a distance of 10 meter. Thereafter, she gets progressively tired and her applied force reduces linearly with a distance to 50 Newton. So total distance by which the trunk has been moved is 20 meters. So total distance is 20 meter. So plot the force applied by the woman and the frictional force, which is 50 Newton also. So calculate the work done by the two forces over 20 meter. So we want to calculate here net work done for the variable force. Let us imagine a figure or sketch for this situation. बघा विचार करा, यस 10 मीटर साठी फोर्स किती आहे 100 न्यूटन आहे, पण त्यानंतर फोर्स किती झालाय 50 न्यूटन. एकूण डिस्टन्स किती आहे 20 मीटर आहे. बघा एकूण डिस्टन्स किती आहे 20 मीटर आहे. एकूण डिस्टन्स बघा इथे 20 मीटर आहे. सो 10 मीटर, yes 10 meter is a force applied for 100 Newton. So that will be a straight line. Then force reduces, means there is a yes cross line. You have to draw this. बघा ही situation draw करूयात आपण. Plot केला आपल्याला काढता येईल. So let us take along this axis. Okay, this take one of the axis and this is another axis. Okay, this is positive side. Say this is positive side, this is negative side. Okay, so along this force is taken, force F along this, yes very good, displacement is taken. बघा काय होत आहे 10 मीटर पर्यंत हा झिरो डिस्प्लेसमेंट आहे. सपोज दिस इज 10 मीटर अँड दिस इज 20 मीटर. ओके, बघा 10 मीटर पर्यंत काय होत आहे 10 मीटर पर्यंत फोर्स 100 न्यूटन दिला आपल्याला. Okay, a woman pushes a trunk on a railway platform which has a rough surface. She supplies a force of 100 Newton over a distance of बघा इथे दिसतंय 10 meter. So therefore I must draw like this. Okay, this is 100 Newton. Then what happens? Force becomes 50 Newton. म्हणजे ह्याच्या हाफ होते. ओके, पण ते कुठपर्यंत असताना yes very good 20 मीटर पर्यंत. So this force is 50 Newton. This force is 100 Newton up to this point. And here 50 न्यूटन. आता हा जो फ्रिक्शनल फोर्स आहे तो कंटिन्युअसली याला अपोज करणार आहे. मग तो 100 न्यूटन फोर्स असो किंवा 50 न्यूटन फोर्स असो, कंटिन्युअसली त्यांनी मॅग्निट्यूड दिले त्याचा ॲव्हरेज फ्रिक्शनल फोर्स विच इज 50 न्यूटन, विच इज मे बी अजून अ कॉन्स्टंट. सो देअरफॉर इफ यू ड्रा अ फ्रिक्शनल फोर्स हिअर, सो दॅट विल बी अ लाईक दिस. म्हणजे हा फ्रिक्शनल फोर्स जो आहे बघा आपण निगेटिव्ह साईडला घेतलाय बिकॉज इट अपोजेस अ वर्क डन. सो दिस व्हॅल्यू, okay, this value is nothing but yes very good minus 50 Newton, or you can say only 50 here. Okay, this side is a minus, magnitude is 50. So this is a frictional force, this is a frictional force, and this is a applied force, this one is a applied force. Okay, बघा आता नेट वर्क डन काढायचं आहे तर फ्रिक्शनल फोर्स काय करेल, yes अपोज करेल. Frictional force always opposes. So work done by the force F applied by the woman is nothing but area of this rectangle. Okay, area of this rectangle plus area of this trapezium. Okay, you can call it trapezium. So this is a rectangle, this is a rectangle, and this is a trapezium. Okay, and this is again a rectangle. We have to minus this rectangle. So net work done is what becomes. So net work done becomes C. Net work done or work done, total work done we can call it. Okay, work done for this case is work done of rectangle of 100 Newton plus बघा rectangle of किती न्यूटन चा तो 100 Newton height चा plus rectangle of this trapezium minus work done of frictional force, that is another rectangle of 50 Newton. So this is story of the problem. So we have to take Work done by 100 Newton, area of the rectangle. That area of rectangle काय असणार आहे? Height is what? 100 and distance is 10. So we have to take like this 100 into 10. Okay. For yes, area of trapezium half. Parallel side कोणते बघा, ह्या parallel side त्यांची addition असते. What is the formula for yes, if you consider this A, this consider yes B, and this height consider as a, if suppose this distance consider as a h, then area for the trapezium always equal to, remember, 1 by 2 A plus B into h. Okay, so this h is 10 here, 20 minus 10, A is 100, B is 50, that is why it becomes 100 plus 50. Yes, this will be a 10, and plus work done by a frictional force. Is it plus or minus? Yes, very good, minus. So minus, what is the height of the triangle? The height of the rectangle is 50 and this distance is 20 meter. Okay, so this whole calculation gives answer, and that will becomes, that is minus 1000 kilogram. Okay, so this becomes minus 1000 joule, sorry, 1000 joule. So this is a total value is what? Is it correct or not? It's not correct because it become minus. So answer will be 1. Do this calculation, 100 into 10 plus 1 by 200 plus into 10 minus this 50 into 20, that becomes a minus 1000 joule. But final answer is 1750. I think calculation करायची. So it will be a 1750 minus 1000. Okay, so this is correct. 750 joule is a net work done. Okay, net work done is a 750 joule, not a 1000 joule. Sorry for this. Work done is nothing but 750 joule is by the two forces over the total journey of 20 meters. So in this way we can draw a situation, a physical situation, in the form of graph. So this is example again a variable force, because magnitude varies from 100 to, yes, very good, 100 to 50 it varies. Okay, frictional force is constant, it's okay, but here applied force is varying its magnitude, changes its magnitude. So this is example of a variable force. A particle moves along the x-axis from x equal to 0 to x equal to 5 meter under the influence of force given by, yes, 7 minus 2x plus 3x square. So this is typically a format of the variable force which depends upon the x. Remember, if you change value of x, the force will be a change. At x 1 meter, at x 2 meter, it will be different. So that is why this is called variable force. So find the work done in the process. So we want to calculate simply work done from limit x to 0 to 5. So this is totally a mathematical dish. So x equal to 0, x equal to 5 meter. So we want to calculate here. So what is this then? Work done is equal to, typically formula is known to you for work done. In this such case, work done is equal to integration from, yes, 0 to 5 f dx. So simple, f dx. So it becomes 0 to 5 f dx, that is 7 minus 2x. Remember, this is 3x square, not a 3x2. Okay, 3x square dx. So we have to take integration of this now. 0 to 5 is the limit. So 7x minus 2x square by 2 plus 3x cube by a 3. Okay, and we have to put limit here now. So it becomes, after putting a limit, okay, 0 to 5. So work done is equal to, in bracket, this is 7 into higher limit is 5 minus 2 into 5 square by 2 plus 3 into 5 cube by 3, and finally minus 0, because yes, every value is multiplied by x, that becomes 0. So this whole calculation gives us 135 joule. So 135 joule is a final answer for this. Okay, so for such mathematical problem you have to do this mathematical treatment. The limits are given to you and you have to take an integration, definite integral for calculation of work done. So force equal to A plus Bx acts on a particle in the x direction where A and B are constant. Find the work done by this force during a displacement from x equal to 0 to x equal to d. So again a typical example of this work done. Okay, so we know that what is this work done. चला फटकन करून घेऊ आपण याला. Work done is equal to, yes, work done is equal to, this limit is 0 to d f dx. Okay, f dx. So that gives us yes, very good, 0 to d and value is given to a plus bx dx. Again 0 to d limit, so it becomes ax plus bx square by 2. Okay, so finally after putting limit, w is equal to, yes, if we put limit here, it becomes ad plus bd square by 2. Okay, after putting a limit means this step, this is 0 to d ax plus bs square by 2. Okay, after putting d here, so minus 0 because multiply 0 0. So work done, finally what becomes it in simplest form, if you take a d common, a plus bd by 2 in bracket, common bracket, that is d. So this gives a work done by this variable force, a plus bx force. The relationship between force and position of a body is shown in figure. The work done by the force in displacing a body from x equal to 1 centimeter to x equal to 5 centimeter is in erg. So we want to calculate in erg. So that is another unit of work done. Okay, we have dealt with a joule. What is a joule? It is a unit of work in, remember, in SI form, and it is, yes, put after the name of scientist Joule. So 1 joule of work is what? 1 joule of work, if you write mathematically, 1 joule of work. Okay, 1 joule of work. 1 joule of work. Okay, that is given by a 1 Newton force. Means what? 1 joule of work is nothing but what? When a force of 1 Newton displaces a body through a distance of 1 meter in a one direction, its own direction, nothing but. So that is, so that's why 1 joule, you know, 1 joule is equal to 1 Newton into 1 meter. So this gives us a 1 joule. But what about the erg? So similarly, erg is a CGS unit. So 1 erg of work is said to be done if a force of 1 dyne, so that is a unit of force, another unit of force in CGS system, 1 dyne displaces a body through a distance of 1 centimeter in its given direction. So therefore on the same line we can put 1 erg is equal to 1 dyne into 1 centimeter. Okay, 1 centimeter. So that gives us a dyne. So erg is that. So we want to calculate in this form. So in this case, force is given in a dyne, that is 20 dyne, 10 dyne and minus 20 dyne. And these values 1, 3, 4 are all in centimeters. So this is how to calculate in erg. बघा आता आपण ह्याच्यात शिकतो आहेत तर मग आपण जूल आणि येस आर्कचं पण रिलेशन पाहून घेऊयात. सो 1 जूल इज इक्वल टू 1 न्यूटन into, yes, 1 meter, and if you want to calculate that, 10 raised to 5 a dyne. Okay, because yes, 1 Newton is equal to 10 raised to 5 dyne. Okay, so you can get relationship between the joule and erg also. So 10 raised to 5 dyne, 1 meter is 10 raised to 2 centimeter. 1 meter is equal to, so this total gives us a 10 raised to 7 dyne centimeter, and that is nothing but erg. So it gives us 1 joule is equal to 1 joule is equal to, yes, very good, 10 to the power 7 erg. So this is relationship between joule and erg. Okay, somewhere we can use this value. So 1 joule is equal to 10 to the power 7 erg. Okay, 10 to the power 7 erg is the relationship between joule and erg. So in this case, it is a straightforward. We want to calculate erg. There is no need of conversion, but we have to calculate, yes, work done for this case. So work done is nothing but what? Yes, work done is the area of this particular diagram, but up to 5 we want here. So this area we want to calculate. So we are having a 4 rectangles here. So rectangle of this size, this is 2, this value is 2. So 2, 3, 4, 5, and everywhere this displacement is given to you, and its height nothing but force in dyne 10. This force in dyne is 20 dyne, and this force also, yes, 20 dyne. So we have to calculate area, total area for the answer. Okay, let us calculate area. 5 centimeter पर्यंत काढायचं आपल्याला 1, that's why 1 work done up to 1 to 5 centimeters. So that gives is, let us say this A, okay, this is A, this is suppose B, C and D. So that net work done required is given by W work done A plus work done B minus work done C, and again plus work done D. Okay, work done A is nothing but 10, its height, and base is 1, plus for B it is 20 into 1. See this 20, height of this second rectangle, 20, minus for this rectangle 20 into 1, and plus final value is this 5 minus 4, 1, again 10 into 1. Okay, so this is so simple. This calculation gives a value 20, and which is, remember, in erg, because we have taken this in dyne, this is in dyne, so this is in centimeter. So work done is 20 erg, or if want to calculate in joule form, so we know that 1 joule is equal to 10 to the power 7 erg. So this 20 erg, how much? Okay, 20. So that work done is given by 20 into 1, 20 into 1 divided by 10 is to the power 7, nothing but 10 to the power minus 7 joule. If you want in joule, so in this way you can also convert this. Okay, this बघा आपण या पूर्ण लेक्चर मध्ये काय शिकलो? वर्क डन बाय व्हेरिएबल फोर्स. So work done, how to calculate work done for the force which is change in magnitude. Okay, direction change अजून आला नाही problem, but varying in the magnitude also. So here also see for 1 meter it is 10, for a second meter it goes 20, then again minus, and like that. So this is how to calculate work done by a variable force. Either you can calculate using area, or you can calculate by the definite integrals, or we can directly, if you having the delta x for each force, then you can add them like that values. The first problem that gives us. So 3 forms are there. You can calculate if work done by each force is known to you. You have to add and subtract as per the, yes, their sign conventions. Second thing, how to using area. So area of that particular diagram is gives a work done. And third thing, that is a simple way, that is a definite integral between the limits given to you, between the displacement limit given to you. So now moving to in the next lecture about the work energy theorem for variable force. So we have slightly derived it in work energy principle for the constant force, but remember we have to derive again it. So there is no any change in the theorem of work energy principle. So you know left hand side contains work done and right hand side contains, yes, change in kinetic energy. But this work done at the left hand side you can calculate by these means, either area, either adding areas, adding work done, or definite integral. But there is no subsequent change in the, yes, kinetic energy. Delta K you can calculate easily. So work energy principle for constant force and for variable force is not so different, but treatment is different. So that's why some mathematics required for the work energy principle for the variable force. Okay, then let us move to a work energy theorem for variable force.